So hi guys, welcome back to my channel. Today we're going to tackle University Physics with Modern Physics, Volume 1, 14th edition, and this book is by U.D. Young and Roger A. Friedman. So we're going to tackle exercises and practice problems tutorial. So we're at chapter 10, Dynamics of Rotational Motion. So I'm going to give you three problems for this tutorial, for this practice problem set. So let's head on with the video. So for our first problem, three forces are applied to a wheel of radius 0.350 meters as shown in the figure on the right side. One force is perpendicular to the rim, one is tangent to it, and the other one makes a 40-degree angle with the radius. What is the net torque on the wheel due to these three forces for an axis perpendicular to the wheel and passing through its center? So as you can see in the figure on the right side, so there are three forces shown in the figure. So the first force is at the top of the wheel, pointing downwards. The 11.9 newtons pointing downwards, while the other force makes a 40-degree angle with the circle, and the value of its force is 14.6 newtons, while the third force that is applied to the wheel has a value of 8.50 newtons. So the problem is asking what is the net torque on the wheel due to the three forces for an axis perpendicular to the wheel and passing through its center. So given these values, we will use the formula for torque. So torque is equals to force times the length of the force times the length or radius of the wheel. But since it's angled, we have to use radius times force times sine phi, and this is based on the right hand rule. So for the 11.9 newton force, for the first one, we have zero radius because the force is perpendicular to the wheel, to the position of the wheel, and or the rotation of the wheel. And the other one is for the second force, 14.6 newtons. Its radius is 0.350 meters, and its phi is, or angle is, 40 degrees. And for the last force, 8.50 newtons, its radius is 0.350 meters, the same with the second force, and its phi is 90 degrees because the force is perpendicular with the radius of the circle. So with that, the torque of the first force is 0, because its radius is 0. So if you use the formula, if you input 0 times the force, or 11.9 newtons, times sine phi, you'll get a value of 0. So for the second force, the value is negative because the rotation of the wheel is clockwise. So negative 14.6 newtons times its radius, which is 0.350 meters, times sine 40 degrees because of the angle of the force. So computing that, we would get negative 3.285 newtons per meter. Times meter. And for the third force, we will compute for its torque. So it's positive because the force is applied counterclockwise, in a counterclockwise manner. So 8.50 newtons times 0.350 meters, same with the other one because it's the same wheel with the same radius, times sine 90 degrees. So we would get 2.975 newton meters. So the problem is asking for the net torque. So we would get the summation of the three torques. So negative 3.285 newton meter plus 2.975 newton meters. So we would get negative 0.31 newton meter, or newton times meter. So the net torque would be 0.31 newtons times meter. Since the value is negative, we know that the rotation of the wheel is clockwise. So we're done with problem 1. Let's proceed to problem 2. For the problem 2, a wheel rotates without friction about a stationary horizontal axis at the center of the wheel. A constant tangential force equal to 80 newtons is applied to the rim of the wheel. The wheel has radius 0.120 meters. Starting from rest, the wheel has an angular speed of 12 revolutions per second after 2 seconds. What is the moment of inertia of the wheel? For this problem, since it's stated in the problem that it has a constant tangential force, meaning that our alpha is constant, we would use one of the four formulas for constant acceleration. So we would use this final angular velocity is equals to initial angular velocity plus alpha times time. So the summation of the torque is equals to the inertia times alpha z. So this applies to the wheel. So for our initial angular velocity is 0. And remember that when we solve for the angular velocity, we need to convert it into radians per second units. So 12 revolution is equals to 75.40 radians per second. So with this formula, first we would get the alpha z, which is its formula is equals to final angular velocity minus initial angular velocity divided by time. So our final is angular velocity is 75.40 radians per second minus 0 over 2 seconds. We would get 37.70 radians per second squared. So that's the acceleration. Then for the inertia, using the formula for the torque is equal to inertia times alpha z. So we know that the formula of torque is force times radius. So using this with a little bit of algebra, we would get inertia is equals to F times R, or torque, over alpha z. So we plug in the values 80 newtons times 0.120 meters over 37.70 radians per second squared. We would get 0.225 kilograms times meter squared. So that's for problem 2. So for problem 3, let's proceed to problem 3. An engine delivers 175 horsepower to an aircraft propeller at 2,400 revolutions per minute. So we have two questions. How much torque does the aircraft engine provide? And how much work does the engine do in one revolution of the propeller? So for the first question, how much torque does the aircraft engine provide? So since we're given power and the angular velocity, we would use power is equals to torque times angular velocity. So remember again that we need to convert horsepower into watts, and using the angular velocity units from revolutions per minute to radians per second. So using these conversion ratios, which is 1 horsepower is equals to 746 watts, and pi radians per second is equals to 30 revolutions per minute. 1 revolution is equals to 2 pi radians. We will use this later for letter B for the second question. So with a little bit of algebra, we will isolate torque. So torque is equals to power over angular velocity. So 175 horsepower times 746 watts over 1 horsepower divided by 2,400 revolutions per minute times pi radians per second divided by 30 revolutions per minute. So we would get the value of the torque is 519 newtons meters. So for the next question, so how much work does the engine do in one revolution of the propeller? So we would use the formula for work. Work is equal to torque times change in radians. So plugging in the result from the previous question, so torque is equal to 590 newton times meter times 2 pi radians, because it's 1 revolution, is equals to 3,260 joules. So that's for problem 3. So thank you for watching this video, guys. I hope that you all learned something about dynamics of rotational motion.